Okay, let's continue to our research work. Okay, as you may know that natural rubber or NR latex can be obtained from tapping heavy siliceous tree here, and then the latex will flow like a milk into the bowl here. NR latex is heterogeneous system which contain the rubber particles here which the rubber particles is a cis-1,4 polyisopene. They are suspending in an aqueous medium. The black spots here are the rubber particles. They are in the cytoplasm because this is the nucleus. These rubber particles are stabilized by the natural stabilizer or the non-rubber part, or you can precisely call protein or phospholipid. This is the TEM image of deproteinized NR cross-linked by gamma ray. The brokenness of their membrane indicated the absence of protein. So we can say that the protein were deposited in the form of cluster on the surface of rubber particles. Okay. After tapping, the fresh NR latex cannot be directly used to produce these thin film products, such as condom, balloons, or glove here. This fresh NR latex needs to be centrifuged to give the concentrate latex over there. And then the skim latex here was obtained in the bottom as the byproduct. This skim latex, we will use this one in the second part of our work. And then the concentrate latex here was then pre-organized or cross-linked and give the network structure inside each rubber particles. This slide shows the method to investigate the morphologies of pre-organized NR latex particles. The method to use to pre-organize the rubber particles are sulfur, gamma irradiations, and peroxide. Among these three methods, sulfur and gamma irradiations provide a homogeneous network structure, as you can see from these 10 images. However, dense network near the particle surface over there were obtained from using peroxide. So, in this work, we selected the sulfur pre-organized to use because of these reasons and because it had the lower cost. Okay. After pre-organized the NR latex with the sulfur, we call the obtained NR latex with the sulfur pre-organized natural rubber or SPNR. This process will increase the film hardness as well as the tensile strength here. However, some problem will still occur, which is soft and tacky here. As you can see from that, it is difficult to insert your hand or your finger into the groove. Moreover, it can cause the protein allergy over there to some hypersensitive user. So, the surface of SPNR latex groove needs to be modified. Normally, lubricating powder are generally used to reduce the surface friction. The example of lubricating powder is a talc or cornstarch. However, this kind of lubricating powder can be easily loosed from the groove, and then it causes the contamination of some kind of field work, such as in electronic or in biomedical applications. Moreover, it can cause the internal irritation to some patients. So we need to mimic that system. And then if we want to solve the problem that I have just mentioned, we prepare the hard polymethyl methacrylate over there, or PMMA particles, and then deposit that onto the SPNR film. The positive charges of SPNR film were generated by grafting polyacrylamide here in the red color by applying the plasma, followed by the UV irradiations. And then these coated particles will increase the surface roughness, whereas in the same time reduce the surface friction. After coated that particles onto the grafted SPNR film, these same images was confirmed the successfully coated of these particles. Moreover, even we stretched our sample for about 7 cycles, the surface coverage here, where this value will not be significantly decreased. So this means the physical properties of our sample is still remain. This slide, in addition, the surface roughness of our rubber sheet after coating with the PMA particles will measure by AFM. As you can see, if you increase the percentage coverage from 12 to about 14, this surface roughness will be increased. And if you notice at the same percentage coverage here, the higher surface roughness will be obtained when you coated the rubber sheet with the larger particles. Moreover, when you coated the rubber sheet with a mix of large and small particles, the surface roughness will be further increased with the higher amounts, as you can see here. This graph shows the relationship between the surface roughness here and the particle size of PMA. This axis is the friction coefficient, which can be measured by that apparatus. As expected, the surface roughness increase while decrease the friction coefficient while increase the particle size. So we can improve the problem that I have just mentioned before by replacing the lubricating powder with the PMA particles. In order to reduce the step of preparations, the PMA particles need to be directly deposited onto the ungrafted SPNR film. To do that, these PMA particles need to be covered or stabilized by the cationic polymer, which in this case is chitosan. Why chitosan? It's because chitosan is cationic polymer. Chitosan can generate the positive charges, which can interact with the negative charge from the non-rubber part that stay on the surface of SPNR film at pH 2. Moreover, chitosan is non-toxic, biodegradable, and have antibacterial activity because of this positive charge. After coated PMA chitosan particles onto the SPNR film, the surface roughness here was increased because of these particles. Moreover, the cytotoxicity after coated with PMA chitosan particles was also reduced. This because the direct contact between our skin and the rubber sheet was avoided. However, the clear zone which indicated the antibacterial activity was still not observed. Why it become like that? It's probably because chitosan cannot generate the positive charges at the neutral pH that was used when we test the antibacterial test from agar test diffusion. Okay. So this is why we move from chitosan to TMC, or NNN trimethyl chitosan. TMC is derivative of chitosan. It can soluble in the wider pH range, while chitosan can dissolve only at acidic pH. Moreover, TMC had higher antibacterial activity. As you can see from that picture, which shows the antibacterial activity of both chitosan and TMC against Sesorians. Both cases shows the antibacterial activity by the appearance of the clear zone. However, the lower amount of as you can see, the lower amount of MIC, or minimum inhibitory concentrations of TMC, was twice lower than chitosan, which means TMC had higher antibacterial activity than chitosan. However, the amount of TMC on the surface of PMA, as you can see from that TEM images, is still low. So, in order to increase the amount of TMC onto the surface of PMA particles, we need to fabricate the raspberry-like particles and then use as substrate for absorption the TMC. This morphology is interesting and important because it had a higher surface roughness and the surface area. This morphology can be fabricated by two approaches, The first one is heterocoagulation technique. In this technique, the small particles here will adhere onto the surface of the larger particles by this driving force, electrostatic interaction, hydrophobic interaction, and hydrogen bonding. And in the second approach, which is Pickering emulsion polymerizations, the small solid particles will adhere onto the polymer particles. These solid particles will act as the Pickering stabilizer for stabilizing the polymer particles. And in this work, we selected the second approach to fabricate the PMA silica nanoparticles while using the silica nanoparticles here as shown in the black color as the Pickering stabilizer. And these particles were then absorbed the TMC. After that, these particles were coated onto the surface of SPNR film. With a similar result from the previous slide, after coated with this composite, the surface roughness was increased here, as you can see. But in this time, the antibacterial activity against Asorians was shown. This because of the chitosan. But the antibacterial activity test is not appear in the case of E. coli. It's probably because of the difference of morphology between these two bacteria, gram-negative and gram-positive.
For the second part, we will talk about a medical glove containing disinfectant nanocapsules. As you know, a medical personnel wears latex glove to protect his hand from direct contact with patients. However, during surgery or patient treatment, small accidents or a needle punctures might occur, which would lead to viral infections of medical personnel. So, Basnell and his team developed special glove containing droplets of disinfectant agent in the glove. When a needle punctured the glove, disinfectant agent was released and neutralized any infection agent carried by the needle. And unfortunately, in this work, synthetic rubber was used to make the glove. So, if a medical personnel wear this type of glove, it's difficult to use or carry a small equipment like a needle. So, we developed a new model for glove containing disinfectant agent. We used NR instead of synthetic rubber, and we used nanocapsule to encapsulate disinfectant agent inside the nanocapsule and then insert it into the glove. And chlorhexidine digluconate or CSD was chosen to use as disinfectant agent in our work. As shown in this chemical structure, CSD has an activity against gram-positive and gram-negative bacteria. So, in our work, an aqueous corn nanocapsule was prepared at this model. This is CSD molecule dissolved in our aqueous phase and surrounded by polymer shell. Now, we show you how to prepare nanocapsules. First, CSD an aqueous solution of CSD was dispersed in an organic medium of dichloromethane and cyclohexane mixture. And in this medium, phosphatidyl was used as surfactant, and polymethyl acrylate or PMA was used for shell formation. After heating at 50 degrees Celsius, dichloromethane was evaporated and led to precipitation of PMA form continuous phase and depositions on an aqueous droplet of CSD. Oh, sorry. And this is the morphology of the polymeric nanocapsule that we obtained from this step. And finally, nanocapsules were redispersed in aqueous phase and ready to use in the next step. From our research, we can prepare the growth containing disinfectant nanocapsule by only 3 steps. First, the mold was dipped into gamma radiation vulcanized NR or RVNR, then into disinfectant nanocapsule in the second step, and into NR latex again in the final step. Finally, we can prepare 3 layers thin film that containing disinfectant nanocapsule in the middle part of the gulf that sandwiched by RVNR film. However, we would like to reduce the preparation step of medical gauze that containing disinfectant nanocapsules. So we modify nanocapsule by coating the surface of nanocapsule with latex layer before insertion into the growth, and we use sulfur p vulcanized or sulfur p vulcanized skim or SPVS particles to coat on PMA nanocapsule. And why we use SPVS particle? Because this skim particle has a smaller size than an latex particle. And when we attach this skim particle onto the PMA nanocapsule, we can obtain the particle like this figure. And then after the skim particle fuse together, we obtain core shell structure particle, and this is the TM image of core shell structure. And for the driving force of this method is because SP is for the driving force of heterocoagulation method. It comes from the interpolymer complex between polyethylene oxide PEO part that coat on the surface of PMA nanocapsule and the surfactant on the SPVS particles. If you want to calculate the theoretical number of shell particles required to form closed pack, monolayer or a core particle on Nmax, you can calculate that by this equation, where RC and RS are radii of core and shell particle respectively. By this method, we can prepare 3-layer thin film of from this method, we can prepare medical growth that containing disinfectant nanocapsule inside the globe by only 2 steps. First, the mold dip into sulfur p vulcanite and latex, and then dip into nanocapsule skim composite latex in the second step. And we obtain the film like this model. And this method is easier and faster than the previous study. From our study, we can conclude that we successfully prepare special growth with antibacterial activity, growth having low friction, surface friction, and growth containing disinfectant nanocapsules. And finally, I would like to thank granting agencies, OHEX, TRF, NSTDA, and TGIS. And thank you for your kind attention.